Yeah, or Gartrell, or whatever, or that guy.
Hello again. We are starting on time. Hooray! We have Alex and we have some, wow, okay, cool. Running Python in the Linux kernel with staff. Awesome.
Yay. All right, thanks for coming. Hopefully this is an interesting talk, and there'll be lots of time for questions later. So the agenda today, we're going to talk about who I am, very briefly, I promise. Overview of what BPF is, the Python virtual machine, this transpiling thing, and then we're done, and that'll be really exciting. So who am I? My name is Alex Gartrell. I am a software engineer at Facebook. I've worked on a bunch of different infrastructure stuff, for lack of a better description. So things like caches and Linux kernel networks and whatever, really a grab bag. And I love my job because it lets me essentially just jump into something I don't understand, do it pretty poorly, learn a lot, and move on. And so if you're interested in a job like that, you should come to Facebook. I am not a compilers expert, and I say that emphatically. There was a compilers course in my university, and I did not take it. I have a really loud compilers friend who talks all the time, Mark Honenberg, I think he's here. And that is literally all I know. So the fact that this works is magic. What I say is nonsense. It's just there's a bunch of cool stuff I discovered and I wanted to share it with you. So a brief overview. Let's watch some programs start. So I wrote this script. It's a little dark, but you can see stuff scrolling by. Essentially what this does is every time a program is executed on this virtual machine, it just prints out, kind of what the first couple arguments are. So it's pretty useful if you're trying to figure out who's starting a bad program and other stuff like that. We use it all the time in trying to debug infrastructure problems at Facebook, right? So how are we doing that? This is where things get magical. So you have your super intense kernel software thing, right? Which calls the system call. And then it really, in real time, just puts a go-to right in the middle, right? Everyone's favorite programmer trick. And it does this in a way where it's safe and it doesn't mess with CPUs and it's super awesome. And then when it does that, it executes some code that you specify, and we're able to create an exec probe that reads the output of that code, essentially, in a mechanism I'll explain later. Now, what's really cool about this approach in particular is that the probe itself is also pure Python. And the bulk of this talk is really how that kind of came to pass. Obviously, you don't have the Python interpreter in the kernel, so you kind of have to play some games. What is the kernel? This is kind of an introductory level talk, so I better describe it, right? So the kernel is the piece right between your user processes and all your hardware and stuff. System calls go into the kernel, things like open this file, write to the network, and then interrupts come up from the hardware. And so you can really just imagine the most complicated, convoluted Node.js app ever, and it's that but in C with no safety. And so it's a terrifying thing, it really is. The constraints of the kernel environment, it's really giant, really complicated. The people that work on this and are able to do it for way longer than I could are huge badasses. They're awesome people. You have full access to everything because you kind of make the rules. And if you have a bug, you can cause a system crash. You can totally break security. You can get famous fast because the Linux kernel is everywhere. So how can we look at it without kind of falling into the sandpit and death and fire and disaster, right? So some history, right? The Berkeley Packet Filter. Imagine that you're trying to load Facebook.com, it's not working, you don't really know why. The thing you can do is look at the network. And what does that mean? Well, you're actually running a utility called TCP dump, and these packets are coming by, and if you know enough about networks, you can kind of say okay, well, I expected a response to this DNS query, or clearly this HTTP connection is timing out Y, and you can learn a lot and start trying to fix stuff. So the way that this actually is implemented is you've got all of your packets flowing through the kernel, this big scary async app, and you open a special type of socket called a packet socket, and then the packets, just these small ranges of data, get handed up, and then your application kind of makes sense of them. Now, the problem with this approach is that modern NICs, or network interface cards, are really, really fast, millions and millions of packets per second. And so you just blow everything up. Your application can't keep up, it gets really confused, you drop packets, and maybe you don't know what's going on. And so there was a simple solution, right? We only care about some of the packets, and the example I showed you was only port 80. And so let's just filter them in the kernel. It's pretty trivial, right? It's ports, whatever. Spoiler, it's not trivial. Building packet filters is hard. So there are lots and lots of network protocols. TCP, UDP, like all the stuff you've heard of, and then it's all nested, and then there are like custom cool protocols that people write to be really fast, like Quick and Thrift and other awesome names. And you need to dynamically match on ranges of bytes that actually change depending on the outer wrapping. So for example, oh, I'm just looking at a TCP packet. Well, you're in an IPv4 packet, which means the offset's here. Or maybe you're IPv6, or maybe something else totally different. And there just isn't a general purpose way of saying, hey, just match on this arbitrary magical thing, unless you want to push new kernels that know about everything all the time. And so the BSD folks did this really cool thing. One option that you can do is you just give it a function, right? You just like, hey, run this like assembly, it'll be all right. It's really fast, it's really flexible, and it's really dangerous, right? So not only will your bug bring down the system, or cause it to hang, or maybe you like screw up a while loop and now like you have to reboot the box, and it's in like Virginia, right? But also, you're just opening the door for all kinds of evil, right? Once people are in your kernel, they can really mess with everything. It's like being super, super root. So it's a bad idea. And the answer was the Berkeley Packet Filter. You provide a minimal set of instructions that only do the stuff you care about. You statically verify that the code is valid, and in general ensure that everything looks legit. And then you can translate it to machine code, and then that can be really fast. And so the operations that they built into this thing, load and store, so like pull stuff out, put it into registers. We're going to talk about registers more, but the thing to know about a register is it's essentially a variable, and in Berkeley Packet Filter, you've got two of them, X and A, arbitrarily chosen, I guess. They added some jumps, so like if this is not TCP, skip it. Interestingly, they only did greater than or equal to, greater than, and equal to, because they figured that you could just invert the logic around it. And so it really is a reduced instruction set, saving untold billions of dollars in efficiency or something. The math they had to add was plus, minus, all the normal stuff. And this is because if you actually look at packets, like they're very clever in how they pack bits, and you need to like and stuff together, and then return, which I hope is obvious. And so what happens, right, when you build something really cool is that other people take your really cool thing and then they try to make it do a bunch of other stuff. And this is called scope creep, and that's why we're employed, right? And so it turns out that an in-kernel virtual machine is really useful. And this cool guy, Alexei Storytov, who actually now works at Facebook, really started pushing the envelope. He's like, this should be everywhere, right? And so, somehow it happened. Somehow he did get it everywhere. So he extended BPF. What does that mean? One, he added local memory. So instead of just having two registers to play with, you've got like a whole scratch space. He increased the number of registers from 2 to 10. Now this is not arbitrary. This is actually based off of the number of registers the machine actually has, right? And so the 2 was an artificial limitation for what a lot of servers were running. And added function calls. So these were scary and amazing. Essentially, you could call a helper and like learn things like what is the PID of the calling process. And finally, some shared data structures. So with the Berkeley Packet Filter, you would specify how many bytes of that packet you actually wanted to take out, and that was your only output. Now you could have like a map that you just updated in the kernel, and if you really only care about like metadata, it's actually much faster and much easier. So where can it be used today? Well, I showed you software trace points, this magical jump in the kernel. You can actually apply the same more or less in user space. Socket filter is the obvious and original use case of the Berkeley Packet Filter. Traffic control, and even in the network card. So in my PR foolishness, I did not do this, but I could have maybe built the world's fastest Python load balancer because you just programmed the network card to do what you want. Now that we know about this like wonderful invention, like how do you use it? What's the toolchain like? This is where people start getting really excited. So the primary interface is the BPF compiler collection. Basically, that's Clang with a new backend. You compile your C function with the Clang, and then you get the like nice output. And it was really easy because of Clang structure to add this new backend. You have a Python script that you can then like insert it. There are actually a bunch of different ways, a bunch of different options, and then with C types, you can do magical C types things. C types is a module that lets you kind of examine memory in the raw, and so that's kind of the intermediate layer between these two things. And so, for example, this is like the simple TC. TC is traffic control. It doesn't really matter in the context of this, but you embed C. Sorry, guys. Oh, there we go. So you embed C as like a string, and then you just send it off to a compiler, and then you inject it into your kernel. And it's pretty cool, but I'm a whiner, right? And so I didn't want to have to deal with, like, I couldn't get Clang to build because it was hard. And you know, like, at this point, my level of knowledge about compilers is like, well, if one is bytecode and the other is bytecode, then clearly there's an opportunity here. And there was, kind of. And so how did we make this work? So quick overview of the Python virtual machine. If this is like mind-blowingly interesting, there was actually a really good talk, I believe it was last year that I caught on YouTube, that goes really in depth in how all the opcodes and stuff work. But I'm just going to give a high-level overview, so excuse some hand-waving. So Python bytecode. Essentially, the Python virtual machine is a single magical stack, where like you just push stuff on, pop it off, and you never run out of memory, and you never have to think about anything, and it's really cool, and it's like fully dynamic, and it's all the stuff we love. It's why you can just mock stuff and it works. It's really cool. Each Python bytecode operates on that magical stack, and there's no real concept of the physical machine. Like real machines, the type that you'll typically buy, will have registers and limited memory and all of this. You have to know where stuff goes, and you don't really have to worry about that if you're a Python opcode. So if right now you're panicked because you don't know what a bytecode is, the good news is it's pretty straightforward, right? So Python functions get compiled into bytecode, which is executed on the fly. So the interpreter is interpreting this bytecode and executing it. Lots of good talks actually here so far about this stuff. You can actually examine this bytecode with the dis module. The dis module is like a Swiss Army knife for understanding what's really going on under the covers. So for example, I wrote a func that does attribute loading and max and all of that stuff, and you can kind of see it here. Let's go deeper though on like what a stack-based virtual machine is, because this is something that is a bit confusing at first. So like I said, all operations occur within the stack. So if we take the expression x plus y times z, and if you remember PIMDOS, right, the order of operations, you're gonna end up with something like this, where you push x, push y, push z, multiply, add, and return. So let's run through the example because that's a little bit weird. Push is just stack dot append. Multiply is you pop the two results, you multiply them, and you append that. Add is the same, but adding. And then return is just return stack dot pop, logically. So with some examples, x equals 2, y equals 3, z equals 5. The stack has 2 in it because we pushed it. The stack has 2 and then 3, 2, 3, 5. Push instructions are pretty obvious. You multiply, you pop 5 and 3, and multiply them, put it back. I know I'm kind of belaboring this point, but it's important, so trust me. And then you add the two results, and then you pop that and return it. That's all a stack-based machine is. So that still kind of seems like kind of nonsense, like why would you choose this? So another example of how we actually got there. So if we take x plus y times z, and we actually look at it as a tree, right? At the top we have this add instruction, and then x, and then the other operand of the add is a multiply, and the operands of the multiply are y and z. And so we're gonna do what's called a, oh wow, I don't know. Pre-order, post-order traversal, where essentially we visit the left child, we visit the right child, and then we handle the parent, right? And so walking through, left child, push x, right child, multiply, but that's complicated. So we're recursing, push y, push z, multiply, add. And so now you can kind of see that the value of the stack-based virtual machine is that it's a really easy transformation from the syntax tree to this thing. And that's why we use it. And it ends up being pretty flexible and pretty cool. And finally, the return. So the Python virtual machine in Python, in a totally unworking representation, you've got your program counter, which is just the thing that knows which instruction you're on. You will hit opcodes like load const, which just pushes a const value onto the stack. Return value returns a value from the stack. Binary multiply again, pop, pop, multiply, push, right? Jump absolute updates the program counter, and then jump if true conditionally updates the program counter. And then the other kind of wrinkle here is variables, which are accessed with these instructions, load fast, store fast. And really, that's just putting it into a dict or not. Globals work the exact same way. You're actually referencing a global by its name, and it's just a bigger and scarier dictionary. And there are lots of other ones that I'm not going to bore you with. But actually, the documentation is fantastic. So if this intrigues you, I invite you to go look at the man page whenever. All right, so how do we take that magical Python, which we now all understand with perfect clarity, and convert it into BPF, right? So BPF bytecode overview, or instructions, really. So you have a stack, and it's called a stack, but it's not as if it supports a push or pop operation or anything like that. So it's an array. It's an array of bytes that you can put stuff in sometimes. Most opcodes operate on registers only, so if you want to change something in memory, you explicitly bring it into a register, you change it, and then you push it back out to memory. And then everything has a fixed size and type. We are not in the dynamic duck world anymore. We now have to know where things are, how big they are, where they live, that kind of thing. And additionally, the thing to understand is, like, while this is a bytecode and there is a virtual machine, the way that this works in the common case is it just gets translated over into machine code, so there's like no management happening at all. So we have to make all of these decisions up front. And then one final thing, just for safety and security, you're not allowed to jump back. Because it turns out that if you jump back, then people will get these like spinning beach ball things and get really mad. It's called a soft lockup, and it's when your kernel's really confused for too long, and it's terrible. So you're just no loops. Just simplify our lives. So what are the essential steps to actually go from A to B? Well, first we're going to freeze the Pythonisms in place with constant folding. We love Python because you can monkey patch stuff in whenever you want, but that's not ideal for this environment. So we're just going to freeze it right as we see it. We're going to normalize the stack-based VM to a variable-based one, which sounds really hard, but actually isn't that complicated. We're going to deduce types and allocate space for each variable. And then finally, we're going to like translate the bytecodes. The part that I thought would be all that we have to do ends up being the easiest part. Everything else is more interesting. So constant folding. Let's look at an example. Boring. Okay, so we have a filter. It has an argument that we don't care about, but we're just returning socket.htons. If you're not familiar with what that is, it just kind of converts the byte order of the thing, of a constant, ethpip. This ends up actually being really dynamic in Python. So we're loading the global ethpip, which is magical, right? And then we are loading an attribute from we're loading the global socket, which is, again, could be patched at any time, so we have to reload it from this dictionary and all of this stuff. And none of this is going to translate into what we're actually running in the kernel. So the first thing we do is we just flip all of our load globals into load const. Nope, it is what you say it is forever and ever. And then once we do that, we apply something called constant folding. So for example, socket.htons, we can resolve that now, because it's all const. We call the function with a constant, so we can actually do that. And so now what was, load a module, load an attribute of that module, whatever, is now just, hey, here's a number. And this is really nice and useful because it allows you to write Python that looks like Python instead of insane, like, pre-computed numbers and other terrible stuff. So it really is an important first step. Now that we have gotten rid of all of the stuff that we don't think we'll be able to do later, how do we eliminate the stack? Well, it turns out that because we don't have magical loops anymore, we are forced to build pretty simple programs. And the nice thing about pretty simple programs is that you can trace just every execution path. So if I were a professional, I would do stack analysis and equivalence classes and whatever, but I'm just going to try running it in every potential way and then see what I see. As I run it, I'm going to identify the source instructions for each operation, and then I'm going to normalize all the destinations into variables, basically just merging two things that are actually for the same variable. So I'm kind of reverse engineering that AST to bytecode thing. Okay, so running through an example. I wrote a really important thing here. A times B if B is greater than 0, else 7. This is the scary bytecode. So yeah, we're going to load A, we're going to load B, we're going to load a const, we're going to compare, the things that we kind of talked about before. So one case is that B is less than or equal to 0. So these are the instructions that we run, and we can see that, for example, op3 is pulling from op2 and op1, op4 is pulling from op3, and then op10 is pulling from 8 and, 1, or 8 and 0. And then we just run the other path. And again, a lot of these look the same. Ooh, that one's a little different, right? That's interesting. And so what we've done is we've identified that most of these variables are pretty boring. Single source, single destination, so that's it. But 10 is interesting. 10 can either be sourced from 0 and 8 or 0 and 5. And so what that means is that 5 and 8 need to have the same output variable. And that's really all it is. Now we can do this. We know for each of these things where the variable result is gone, and the stack is gone, right? And so you can actually see that var6 is reused and all the other ones are fresh. And with that, that's like the really big cognitive leap to like understanding how this all works. So now we don't have to worry about a magical stack, and we can get to the business of understanding what we're looking at. So deducing types. Again, doing this for real is very complicated and interesting, but we already have a bunch of things we can take for granted. For example, each variable, each input type we know like that certain operations in this world can only return one thing, right? So compare returns a bool, we know that. And constants obviously have a certain value. Something you don't know when you're actually running Python. And this is why just-in-time compiling real Python is really hard. But if you just are willing to fix all your constants, it gets much easier. So running through, okay, we know the constants are ints. That's easy. We know the arguments. That's just something we have to know in advance. And then we know that certain operations only return certain types. In this world, multiply returns an int. And with that, we know all of our types. And because of C types, we know how big they are. The next step is even easier, right? We just walk through and we, one big scary caveat, primitive types. So if we look here, I have x equals 1, and I call foo on x. Now, logically, I'm passing it as a value. That's not really true, but ints are immutable, so it works. And the other, I'm kind of passing it as a reference. Again, this all works very solidly within Python's type system because anything that you don't want people to change ends up being immutable. But that's not how the machine code works. Now that we're talking about like locations in memory, it matters if I'm using the same address or if I'm making a copy. And so I say that not because we should get into it, but because there's like a bit of like this kind of hand-wavy stuff at the edges where you have to do weird things to make the semantics work. It turns out C is just like different enough from Python that it gets really interesting and fun. But anyway, that tangent aside, let's talk about how we actually decide where these things live in memory. So variables can't magically exist, like I said. They need to live somewhere, pointed to by arguments, and stored on the stack. Those are like the really two bases. So real quick lesson. When you call a function on a x86 64 computer, the first register lives in RDI, and the second register lives in RSI, and that's just something you have to know. It's a calling convention. And so when our thing is invoked, we know that something important is in RDI, and we just have to stash it somewhere. Everything else that we're going to access that isn't an argument, we have to choose where it's going to live. So assigning vars to memory, another example. This is really simple, right? Not super optimal code. We just store the input into C, and then we return C. So the way that we'll, and this is like after type deduction and all of those cool steps, essentially what we're going to do is we're going to take our load fast operations and just convert those into variables. They aren't really opcodes to us anymore. So those are now fast vars. And with those fast vars, we just choose where they live. And there's really interesting ways to do this. Like the right way to do this is to analyze object lifetime and allocate it and free it at the appropriate time and ensure that's all safe. Or you can just use memory really aggressively and greedy, and you just update a pointer and you just use up all of your stack. And so that's what I did, because that was easier. And so once I allocate my fast vars, I just have to allocate space for my other vars. Again, I'm incrementing a counter. And now I just stash with each of these variables where I want the sources to come from and where I want the results to live. So now that we have that information, we know for each opcode where it's coming from and where it's going, we can do this thing called template compilation. This is another shortcut. But if you look at a professional compiler, like a JavaScript core, for example, they will have multiple tiers, where at first they do a really naive compilation because who knows, we might never run that function again. And then as it gets hotter and hotter, they will step it up and do more complicated and interesting optimizations. So we just stop right at level 0. And really what that means is we just take the bytecode and then we translate it. Again, this is kind of the easy part. So the representation is close enough and we can translate it. Really simple example, return value. So this is mildly interesting because, again, the calling convention is different. Return doesn't take an argument, so you just stash it into a special register, RAX, and then you call return, right? Binary multiply is the same. You just load it into register, multiply, and push it out. Right? Compare op, load it into register. One interesting wrinkle here, going way back to BPF. So for efficiency, as you know, they were very efficient with no less than operations. The other thing that they did is they said, anytime anyone's doing a comparison, really they're jumping, so like let's just make that one thing. And so if you want a real comparison, as you need, you actually have to jump to a point where you set a value to 0, or jump to a point where you set a value to 1 and kind of figure it out. And then the other interesting part is shared data structures. So like I said before, some data structures can be shared, things like hash maps, queues, whatever. And so when we look at those shared data structures, you can see here I've written a filter. In that filter, I update based on the protocol of the packet I'm seeing, a counter, just plus equals 1. This doesn't exactly have Python semantics. For example, you would probably get a key error the first time you saw one. So it's kind of collections.default dict-ish. And I'm accessing it as I would a dictionary in the application. This lets you write really intuitive programs that work the way that you think they would, but it's not how it works. The machine code doesn't have a dict type. And so what we're actually doing to make this work is we, in the application, have to reference it by a file descriptor, and then we use a BPF syscall. And so everyone has probably written code that does a set item or a get item or whatever, and that's roughly what I'm doing. In the kernel, though, I have to reference it by pointer, but because I own the whole stack, I just do a quick and dirty type check and say, like, I see what you're doing here, and I'm just going to totally do it behind the scenes. And so in that templating jet thing, I just translate the, like what's inside of this map into a function call, and the user never sees it. And so, again, get item, set item, and then, what is this? Yeah, and to the, when I'm allocating it, because of the way it works, it thinks it's an int, and that's just fine, right? And so this is where Python is magical, because you can't quite hack it like that in any other language. And so, woo, everyone here knows how to build these things, these scary, terrifying things. But there are a lot more things to do. So for example, I talked about how we punted on variable lifetime analysis. I talked about how we punted on higher level abstractions, or I don't know what that is. So we're slow and we're inefficient right now. And that's why you should probably use the C thing for something super critical, but it's really good for tracing. And then there are other higher level abstractions. For this to be really usable by people, they're gonna need to know what RDI is, and that's too hard. And so hopefully we can add strace-like abstractions and make that better for everybody. So I have some demos and stuff, if we're all feeling brave. Thank you, by the way, for enduring me. I'll show some examples. If there are any questions, now is a great time to ask, otherwise I'll just pop up some examples. Oh, yeah, and if you could ask at the microphone. So the question I just got was, how fast is it? Kinda. It's fast enough. The test really is, when you're doing this type of stuff, you look for it in traces. You don't want this to impact system performance, so you don't really have the notion of like how many operations can I do per minute or anything. You just want to ensure that doesn't show up as a profile thing. For most trace points, the code you're executing is so simple that even if you compile it really, really poorly, as I have, it doesn't matter. So fast enough so far.
The constant folding that you mentioned with socket.h2ns, right? You can only do that if you know that socket.h2ns is a pure function. Is that something that is embedded in the compiler? Is that knowledge?
Right, so the point he's raising is I was able to fold the constant socket.h tons, but if I like reversed that comparison and said, oh, I want to flip the byte order of this variable argument thing, it's like not gonna work. And so the answer right now is that there are in addition to all of the helpers you can use, there are some pseudo functions that allow you to do the same. You could pretty trivially map it, so this is like the programmer's dilemma, right? I could transparently under the cover say, hey, this looks like a function I know about, I'm gonna like swap in a kind of a replacement function. But now you raise the question of, do I wanna do something that surprising and scary? So that's to be implemented so far. But yeah, you can't really bring general purpose functions in right now, but there's no reason that you couldn't inline functions, for example, if you want to do that as well. Thank you.
I had one more question.
Okay.
Have you looked at using MyPy or any of the static typing stuff that's happening with Python?
I haven't, no. Yeah, this is really a hobby project. It was a happy accident that Facebook continued to pay me while I worked on my hobby at work, but yeah, I'm many miles to go. And I do intend to open source this as soon as possible so that other people can play with it and actually make it good. But just ran out of time before the conference, unfortunately. Yeah.
You mentioned updating shared data structures. Did you have to do any, did you just ignore the locking, or if you're updating, can these BPFs only be fired from once, or what, how do you make that safe?
Right. Yeah, so the way that, this is kind of going a bit deep into how the kernel works. So Linux kernel has to do a bunch of concurrent stuff all the time, and if it locked too aggressively, you really see the performance hit, and it goes kind of sideways. So they use something called read, create, update, and super hand-waving here, but essentially this is like a very limited garbage collection where it's like, hey, delete this when you're pretty sure that no one's using it again. So the way that BPF works is on the kernel side, they use read, create, update to update the data structures in place. And that allows you to run with the same data structure on all the different cores and not step all over each other and slow it down a lot. And then on the user side, because you're going through the system call, once you're in that system call, it uses the same mechanism. So it's protected in that manner. But otherwise, they've done a lot of the legwork to deal with all the synchronization issues. Cool, any other questions? Complaints? Okay, then let's be brave. This is a really bad idea. There we go. So, just to give you a taste. And it's not mirrored, so this is going to be extra fun. Because slideware is slideware, right? Oh no, the colors are awful. Does anyone have any quick tips to make this less terrible? Other than bigger? Oh, that's okay. So this is the actual thing we're looking at. I showed you this slide. Python 3, of course. I know my audience. Oh, okay, so you can see that tmux is really wasteful and is constantly like, wait, where am I, where am I, where am I? And that's just to get the host name to show you in the bottom corner. But if, for example, you can see the magical functions Firefox opens, and Firefox is mad at me for demoing too much. I happen to trace system calls, which ends up being really interesting. And all the time, a problem that we deal with is some magical script that somebody else wrote comes along and unmounts something that was really important to us, and we don't know why. And so, and of course, it's not logged in a consistent place or anything like that. And so we can just like pop one of these out there and just watch to see who's doing this terrible unmount. So system calls are interesting, but you can put this anywhere at all, really in the kernel, any function that you care about. So if you really want to get deep into why is this specific, who's opening this actual inode, you can do that. Now, one interesting problem, bonus material, that you run into is the types are really complicated. So you go down this rabbit hole and you're like, well, oh, people can open a file by path, but it changes depending on which directory they're in. I can't do a string comparison, right? I'll just look at the inode number. And at that point, you're now digging into a struct that is like very complicated with lots of fields, and you have to replicate that into Python somehow. And so one really terrible thing you can do that is a huge time sink, but really fun, is you just write a dwarf parser, or there's actually an open source one you can use, and you can just pull the data structures right out. And so I encourage you to make everything you possibly can as dynamic as possible for maximum chaos. But yeah, any other questions about any? All right, well, thank you so much. It was a pleasure to talk to you. Overview of what BPF is, the Python virtual machine, this transpiling thing, and then we're done, and that'll be really exciting. So who am I? My name is Alex Gartrell. I am a software engineer at Facebook. I've worked on a bunch of different infrastructure stuff, for lack of a better description. So things like caches and Linux kernel networks and whatever, really a grab bag. And I love my job because it lets me essentially just jump into something I don't understand, do it pretty poorly, learn a lot, and move on. And so if you're interested in a job like that, you should come to Facebook. I am not a compilers expert, and I say that emphatically. There was a compilers course in my university, and I did not take it. I have a really loud compilers friend who talks all the time, Mark Honenberg, I think he's here. And that is literally all I know. So the fact that this works would be used, and it's super awesome. And then when it does that, it executes some code that you specify, and we're able to create an exec probe that reads the output of that code, essentially, in a mechanism I'll explain later. Now, what's really cool about this approach in particular is that the probe itself is also pure Python. And the bulk of this talk is really how that kind of came to pass. Obviously, you don't have the Python interpreter in the kernel, so you kind of have to play some games. What is the kernel? This is kind of an introductory level talk, so I better describe it, right? So the kernel is the piece right between your user processes and all your hardware and stuff. System calls go into the kernel, things like open this file, write to the network, and then interrupts come up from the hardware. And so you can really just imagine like the most complicated, convoluted, like, this is magic, what I say is nonsense, it's just there's a bunch of cool stuff I discovered and I wanted to share it with you. So a brief overview. Let's watch some programs start. So I wrote this script. It's a little dark, but you can see stuff scrolling by. Essentially what this does is every time a program is executed on this virtual machine, it just prints out, kind of what the first couple arguments are. So it's pretty useful if you're trying to figure out who's starting a bad program and other stuff like that. We use it all the time in trying to debug infrastructure problems at Facebook, right? So how are we doing that? This is where things get magical. So you have your like super intense kernel software thing, right? Which calls the system call. And then it really, in real time, just puts a go-to right in the middle, right? Everyone's favorite programmer trick. And it does this in a way where it's safe and it doesn't mess with. Yeah, or Gartrell, or whatever, or that guy.
Hello again. We are starting on time. Hooray! We have Alex and we have some, wow, okay, cool. Running Python in the Linux kernel with stuff. Awesome.
Yay. All right, thanks for coming. Hopefully this is an interesting talk, and there'll be lots of time for questions later. So the agenda today, we're going to talk about who I am, very briefly, I promise. Like, no JS app ever, and it's that, but in C with no safety. And so it's a terrifying thing, it really is. The constraints of the kernel environment, it's really giant, really complicated. Like the people that work on this and are able to do it for way longer than I could are huge badasses. They're awesome people. You have full access to everything because you kind of make the rules. And if you have a bug, you can cause a system crash. You can totally break security. You can get famous fast because like the Linux kernel is everywhere. So how can we look at it without kind of falling into the sandpit and death and fire and disaster, right? So some history, right? The Berkeley Packet Filter. Imagine that you're trying to load facebook.com, it's not working, you don't really know why.